Alright, we are back and we were seeing how to solve for these angles phi A, phi O, and phi N using the cylindrical coordinate system. So first, two videos before this one, I think we solved for these angles phi A, phi O, and phi N, which is the angles of rho, pitch, and yaw, using the Cartesian coordinate system. And it was a suggestion from the book, which is from the author. So we were doing a analysis of the RPY matrix. So we can write this equation for this matrix with these angles. So if we multiply the rotation of rho, pitch, and yaw, we will obtain a total matrix, which is this one, and doing its analysis, we multiply both sides of this equation by a inverse transformation, which is a rotation above the a-axis with the phi A angle. So multiplying the right side of this equation, we can conceal this term, and we are left with this equation. And from the book, the suggestion, it was to consider that this characteristical matrix of the Cartesian coordinate system is our desired final orientation, or final desired orientation. And this way, when we multiply this left side of the equation, we got this matrix, and multiplying this right side of the equation, we got right here the matrices. We obtain this matrix, and this way, as each element on the left side of the equation on the matrix, it has a correspondent on the right side. Each element on the right side is corresponding to, on this matrix, is corresponding to one on the left side. We got a equivalence, as this is a equation. This way we are able to write equations. So for example, this term, this element of this matrix on the left side is equivalent to the 0 on the first column, and on the second line on the right side of the equation on this matrix. So we can write this equation, and we can solve for phi A. So this way we solve for both of these angles, and we solve the example 2.21 from the third edition, but I couldn't find all the angles. I was just able to find, let me see, the angle phi A, but also the angle, I think it's alpha. But solving for phi N, we got it right as well. I think just for no this example, we completely the resolution and we find all the angles. Okay, I think it was for the example 2.22 that we could find all the angles, and I said that solving the example 2.21, and now I'm with the book, so let me see, is the right, is the example 2.21 from the second edition. So I said that as we couldn't find the other angles, we could solve all the example 2.22 from the third edition. We will solve the example 2.21 from the second edition, and the only thing that it changed is the value of the elements on the matrix, which correspond to the coordinates and the coordinates of the orientation and the coordinates of the position. So I think we also and I said that before to solve the example 2.21 from the second edition, we should done a resolution, try to find the angles of rho, pitch, and yaw, but using the cylindrical coordinate matrix. And this is what we've done, and we end up with these solutions. But the problem is if you repair, if you notice, these solutions is a pair of sine and cosine. But the problem is for phi O and phi N, we got 0 as one of the pairs, and this it will result in, if you take the arctangent, it will result in 0 degrees. And even if we switch the positions, just to try to find something, this also will end up with a angle like 90 degrees or 180, and this is not the angles that we got as solution in the book. So these solutions, they are not totally right. I said that the way that we try to solve is correct, because it's the same way that we solve using the matrix for the Cartesian coordinate system. And this way was the second way to solve this type of problem, this type of example, is to find the solution using the respective matrix of the respective coordinate system that we are on. But a good thing, and I will write right here, is that the book, it suggests to use, even for the cylindrical coordinate system, it suggests to us to use the solution that we find for the Cartesian coordinate system. So I will write this because it's useful. So even in let me see, in a coordinate system different from the Cartesian one, we can use its solutions for phi A, phi O, and phi N. Okay, so we got the solutions for the Cartesian coordinate system, and even if we are in a different coordinate system, we can use the solutions for the Cartesian one, which makes our life more easy. And the problem also is that I said we will try to use the solutions, but I'm already saying that if we try to, as this is a pair of sine and cosine coordinates, if we try to use, to take the arctangent using the zero, we will end up with 0 degrees as result, and even if we switch between these components, we will end up with an angle which is different from what is on the book. We will end up with an angle like 108, 90, because since this angle is 0, but again, the way that we are trying to find the solutions is correct. And on the future, if we have the opportunity, because we have so much to cover, we have so much to do, and on the future we can explore more of this with more patience. Okay, so I don't know if I'm forgetting to say something. We can start with the example 2.21 from the second edition. So I will even write the statement, but it's the same as the 2.22 of the third edition. But again, what changed right here is the coordinates of the orientation and the position of this respective matrix. So let me see if I don't use these coordinates. No, okay, so perfect. So is the second edition. Example 2.21. Okay. So it asked to us to find all articulated variables. I think it's joint, all articulated joints. Let me see if this is statement. find unnecessary joint variables. Okay, joint variables. Find unnecessary joint variables. If the robot is a cylindrical plus RPY joint variables. So phi A, phi O, phi N, okay, so we got the total transformation. So as we got the total transformation, we already got the orientation and position of this robot is given by this statement 354, 585 minus 0.788, 0 minus 0.774, 0.722, 0.106, 0, 0.649, 0.475, 0.596, 0, 4.33, 2.5, 8, and 1. And now different from what I was explained to you, we can think this in a different way, as it's because not just because we got this total transformation, but also we can say that because the total transformation is representing this matrix, which is it got the orientation and position of the robot. So the motion of the robot, where the end effector is localized, and it is a cylindrical plus RPY robot. So for the cylindrical system, we got this total transformation. We are in the cylindrical coordinate system, and we are doing applying transformations of translation with some radial, irritation with some alpha angle, and another translation with some L length. And we are multiplying by this matrix of RPY because let me see. Further, we will see that we got different ways to work with RPY matrix, but I already comment that we apply this matrix on the robot because we wanted to change its orientation, position, because we wanted to restore its initial position. So VA, VO, and VN angles. Nice. And now I write something important, and I will try to do the same solution as on the book to be more, so it will be more easy, but something that we already have learned. Right here we got 4 angles, so 4 angles. So we got 4 angles, alpha, VA, VO, and VN. And we have to dissociate them. Coupled angles, they are coupled. Let me see. Coupled angles. And how can we dissociate these angles? How can we decouple these angles? So how can we decouple these angles? Is with a transformation of rotation above the a-axis, applying, and we already got the solution because, as I'm saying right here, even in a coordinate system different from the Cartesian one, we can use its solutions for solve for these angles of VA, VO, and VN. And on the Cartesian coordinate system, we face this problem. I'm sorry. Now this solution it got more complicated than I think it was. Right here we are using the cylindrical coordinate system at the beginning of this solution. And so we start with the spherical one, and we end up using the Cartesian one. So for the spherical one, we use the rotation above the a-axis with some angle. So just for let this clear, I think I can just repeat only the beginning of the solution. How can we decouple these angles? Applying a rotation above or around the a-axis. Okay, so I will repeat the beginning of the solution. So solution for the angles for RPY angles. So let's suppose let me just copy this because it is the same and we just need to repeat, but I only repeat the beginning of the solution, just a theoretical introduction. Okay, so let's suppose that a robot is designed based on the spherical coordinates in RPY. So this way we got 5 angles. We got 5 angles. Beta, gamma, phi A, phi O, and phi N. And to decouple these angles, again, we use this rotation above the a-axis. And now I just need to write this transformation rotation is a rotation above the a-axis, and let's say let me see right here some is the phi A angle, and of course is an inverse transformation. Okay, so the R now analyzing the RPY total is a transformation. Yes. So RPY again multiplying each of these rotations which are made it around of this axis and rotation above n axis x with some phi n angle. Now we will pre-multiply. Let me see. Is a pre-multiplication. And what we are doing right here, when algebraically, when we do this pre-multiplication, geometrically means that we are applying a rotation right here. So this rotation geometrically is a rotation, but algebraically is this transformation. You write this way. So we got right here algebraically and geometrically. Okay. All right. And now these terms, they cancel each other. And I'm just repeating the solution. We have already done this. Okay. And the book from here, it jumps already to this. Now it says that supposing that we wanted that our final position it is on the Cartesian coordinate system, so desired position, orientation and position, desired final desired orientation position. So we got the Cartesian. Let me see something. Yeah, final desired orientation. Cartesian. We also got the spherical. Well, let me see if it's not redundant. If now we said that we wanna that our final desired orientation is on the spherical one. No, this is just a example. And I think that using this spherical one, so we got more than 3 angles, we got couple angles, is already to give us a solution which is a generical solution for all these angles. So I think it works for both. I'm pretty much sure that it had to work for both of these coordinate system and also the spherical cylindrical. Right here I should write cylindrical first, I don't know, cylindrical. Okay. And we find its solutions using the Cartesian one. We already got the solutions because right here we just need to multiply by the matrix of the coordinate system. Coordinate system matrix. So we got the solutions this way. So we find the solutions for the A, the O, and the N. Okay, now this way. Now let's just solve the example. And now I will just use the solution of the book. We are on the cylindrical coordinate system and we got its matrix, the matrix of the cylindrical coordinate system. Cylindrical coordinate matrix. The matrix with the coordinates of the orientation and position. Let me just copy all this. Okay. And again, this is an equation. So we got sine of equal. And each element on the matrix on the left side of the equation, it got a correspondent element on the right side with on the matrix. So we can write, and this way we are able to write equations. Now we will write that R cosine of alpha. For this element, we got 4.33 as a correspondent is the equivalent. So its equivalent is 4.33, and R sine of alpha, its correspondent is its equivalent is equal to 2.5, and we already have solved the example 2.21 from the third edition, which looks just like this one, is very similar. And now we got the relation for the tangent. The tangent is equal sine divided by cosine. So if you wanted to extract the alpha, that is an angle that we will use to find the other solutions. So alpha of tangent is equal, now we can use R sine of alpha divided by R cosine of alpha. So 2.5 divided by 4.33. And now we apply arctangent to extract the angle. So alpha is equal a tan 2, because it's a pair of cosine and sine coordinate. 2.5 and 4.33, which is equal. And now let's use the octave to help us. Okay, I'm already with the octave open, and clear all to clean the octave's memory, CLC to clean the command window. Now we can type alpha bag, which is equal a tan 2d 2.5 and 4.33, which is equal 30 degrees. Okay, M is correct. So 30 degrees. And now I will use some draw that we have made it, so I can explain to you what we will do right now. This draw right here, just the draw we need. Okay, this alpha is a angle of rotation, because we are on the cylindrical coordinate system, and this PA is also a rotation, so we are summing them. Okay, so let me see if we got the solution for phi A. Now we wanted to find phi A, and as we got alpha, we are able to find phi A. let me see. Right here, VA. Okay, and as you can see, I already has changed right here. Now I can even explain better and also affirm what I was doing, trying to find the solutions for these angles using the cylindrical coordinate system. Let me just copy them, and I can do better than this without using the complementary solution. This solution, let me see. This solution, one of the solutions is for the cylindrical one, and other is for the Cartesian one. Okay, now it's right. Nice. And this way I can at least affirm what I was trying to do, and also to show you that it's correct, the path to find the solutions, the way that we are thinking. Okay, so if we are using the Cartesian one, is this matrix. Nice. So the solution for the cylindrical one, and the solution for the Cartesian one, and of course we got for the spherical one also as well. So we will use this one. So the cosine of alpha is 0.354. And for sine of alpha, now sine is 0.505, and now hope is right. It must be. Okay, so phi A is equal now to the octave. Phi A dag is equal 8 10 to the 0.505 and 0.354, which is equal approximately 55 degrees, and this is correct. Nice, 55 degrees. But this 55 degrees, this is for phi A plus alpha, which is equal 55, because is this angle right here, and let me doing this huge arrow right here, and let me do approximation. This angle right here is phi A plus this alpha right here. Okay, I'm sorry for all this mess, but I think it is understandable. Hope it is. Hope you're understanding what I'm trying to explain to you with this. And this angle alpha we have solved it, we find, and is equal 30. So is phi A is equal 55 degrees minus alpha, which is equal 30 degrees. So phi A is equal 25 degrees. Okay. And now we can use the solution again from the beginning. Even in a different coordinate system, different from the Cartesian one, we can use its solution for other coordinate system. As is our case right now, we are using the solutions that we find for the Cartesian one, and you saw that is very similar. The solutions are very similar. The difference right here we were using nx and ny, and it's pretty much the same. Even the coordinates, the position of the matrix, the position of the elements is the same, as you can see. But the problem is the last video when we were solving for the cylindrical one using the cylindrical matrix, of the coordinate system of the cylindrical system. Sorry. Um, we couldn't find the correct solution as we end up with the zeros as one of the pairs of these parameters. Um, so if we take the arctangent using 0, we will end up with an angle equals 0. And even if we switch the position of these parameters of these terms, we will end up with an angle which is very different from what we got on the book. We will end up with 108 or 90, and these angles, they are not correct. And the way that we solve the path is the same that we use for the Cartesian one, so I think it's correct. I'm pretty much sure. But unfortunately, the equations that we write, we end up with the 0, and this is a problem. And also, I'm having a problem with the sign just because of the superscript right here from this inverse transformation. And I'm just being lazy. I could just write the correct transformation applying this sign, but I don't know. As I said, we will discuss this on the future. We have the opportunity because we have so much to do, and I said that we will get out of this with a satisfactory solution, with satisfactory results. And till now, I think we are getting at least correct results from our calculus, from our solutions. So I think we can go on with the content. So let me find the solution for phi O. Okay, right here, the solution for phi O. And at least we can compare with what we got from the solution for the cylindrical one. For the cylindrical one, the solution for phi O that we got was this one. I don't know what is this. T0 right here. Okay. Okay, we can compare. So this NZ, we end up with 0. Sine of phi A, sine of phi A, and right here is nx, but nx, if it's equivalent on the position of the element is equivalent to cosine, and ny on the matrix is equivalent, its position is equivalent to sine of alpha. We can switch these positions, and if we switch the positions, we got the same as we are getting right here. But for let's see the NZ position. NZ position, as you can see, it corresponds to this element, this position on this cylindrical one. So now I'm not sure if I'm wrong, because as I'm seeing, right, the signal is wrong, but the signal right here, I don't know exactly, because comparing, I haven't compared yet. I'm doing this comparison right now with you, and as I'm seeing, it makes sense. So I will I will leave right here, and let's see what we got. Okay, I don't know, because if we use, let me see, now it will be very interesting. But anyways, just for precautions, I will use these solutions first. So we can write, we wanted to know our phi O angle, so is A10 2, and using this as reference, so is equivalent to this position. Okay, and and next is equivalent to cosine of alpha and cosine of alpha in terms of the position of the element. And cosine of phi A, cosine of phi A, and this is always got me. We have solved it for phi A. Phi A is 25 degrees. Okay, so cosine of phi A, cosine of phi A, so is cosine of 25 degrees. So let me already write cosine of 25 degrees plus, and y equals to sine of alpha in terms of position of the element on the matrix, and sine of alpha is equal to this value times sine of alpha, so times sine of phi A, sine of 25. So phi O is equal to A10 to minus 0 point is one of the pairs just solve this first. 0.321 and 0.2134, and summing these terms. Zero point 5344. So VO is equal to 810 minus 0.7880. Okay. To the octave, VO DAG is equal 810 to D minus 0.788 0.5344. And on the book we got 52 degrees, and let me try different feedback. Equal 810 to D 0.35344 minus 0.788. No. And again, I'm not getting the correct result, the same as is on the book. Let me see if I'm doing something wrong. Yeah, I don't know exactly what I'm doing wrong, because I'm not getting on the correct result, at least on the result what is the same as is on the book. Okay, now let's try for Vn. Let's see what we get. For Vn. So first, VA is equivalent on the cylindrical coordinate matrix. Let me see. AY. Yeah, AY is equivalent to 0. Put in terms of element, we got this element right here, this element. Okay. And AX, this is N, this is O, AX. So we got as element this one, AX for AX. Okay, for OX, OY, for OY, which is equivalent to cosine of alpha, but in terms of element, we got this element. And OX, okay, this first one. Wait. OY, OX, right now. OX is equivalent to this term, to this element, or term, it's the same. Okay, let me see something. This element is negative, and right here it is positive. It's negative also. So we got right here a positive sign. Let's see. So I don't know. Oh my gosh. 55, at least is positive. And now I think it's right. I don't know exactly, but now this sign it turns positive because right here is negative. And on the book is 52, but we are doing so much approximations. So we got plus 55 degrees. Okay, let's continue. And now I notice right now I'm looking to this. Okay, so is minus 0.475 times cosine of phi A. Phi A is equal to 25, so it's cosine of 25, which is equal 0.91 plus 0.649 times sine of phi A, so is sine of 25, which is equal 0.423, and this is one of the pairs of these parameters is a pair, and the other pair so is something like 0.722 times cosine of phi A, cosine of phi A, which is equal 0.91 minus, so this is become plus because of this sign, and right here as well. Will become positive because of this minus sign. Okay. So is 0.674 times sine of 25, which is equal 0.423. And this operation 0.722 times 0.91 plus 0.774 times 0.423, which is equal 0.942 approximately. So phi n is equal 810 to 0.707 and 0.942. Okay, let's see what we got. So phi n dag is equal 810 to the 0.707 and 0.942, which is equal 36, and that is wrong. Let's see. This signal was negative. Let me confirm. No, this signal is not negative. Sorry. AY is this element. AY is this element, and this signal is not negative. So right here, I'm doing a operation of sum when I should do a operation of subtraction. So right here is minus. And let me see, right here we got minus also. Right here is minus, okay, plus these values right here, and OX. Let me confirm OX. OX is negative. No, OX on the solution is negative, but in terms of element, the position of the element is what we are looking for. The position of the element OX, it's corresponding on the cylindrical matrix to minus sine of alpha, but we are looking in terms of correspondent, in terms of the element. Right here is minus, so right here is also minus, and this is become plus. So right here is where we are doing wrong. So let's do it again. So let me do 0.649 times 0.423. Now minus 0.475 times 0.91, and we get minus 0.158 with approximation. So right here is minus 158. Minus 0.158. Let's see now. Minus 10 degrees. Yeah. Let me see. AY. Um, AY. AY, this element. Yeah, it's correct. This element. Yeah. Now I'm not, I don't know what I'm doing wrong to get these values. Well, that's a bit sad. That sucks. I'm getting a result which is very different from the book. And okay, so having more time, we will get back on this. So I need to get back on this. Because we need to move on with the content. I think this is the fourth or fifth video in which we are discussing about these RPY angles. Okay, but I hope you understand what I tried to pass to you with this topic. Why we use RPY angles. We will see these angles with more often. And now, moving on, we will entry in early angles. Okay, so this is what we will do from now on the next video. Now we will see Euler's angles. Euler angles. Okay, so this is what we will see on the next video. And to finish this, I think I can do to you a better explanation of this software. Just explain the interface. On the right side menu, you can see right here, follow the pointer and reference frames. So we got the word frame, which is the base. So pay attention on these terms. The terms, they are very important, just like know how to solve the equations, know how to write transformation equations, which is one of the most important things in robotics. Know how to write transformation equations, know what it is transformations, know how to apply all types of transformations, rotation, translation, know the types of robot, articulated ones, um, cylindrical ones, and you saw that we can do a mix with the RPY. So basically I think it's more for the articulated ones. So right here, reference frames, word frame, and if I click right here, we got this arrow, which is the axis. Right here in red, we got other axis, and I think on the top, I think it's the side. So I don't know. I think the blue is the z-axis. The blue is the z-axis, and one of these, the red or the green, is the y, and the other is the x-axis. And we got the frame of the two. Okay, and now let me turn the two. Okay, we can add. So we got 6 frames. So this is a 6-degree of freedom robot. Right here you can see the measures, the lengths, the dimensions of the right here 2 frame. Okay, we can change the angles of the joints. So right here, theta 1, we are doing a rotation, and the problem right here is that this arrow in red, I said that the blue is for the z-axis, and this arrow is pointing, turns to up. Let me see if I do this. Yeah. Okay, so right here on the bottom side, right here on the bottom, on the right, we got a translation along, so we can do a translation along the axis, the x-axis. We can do a translation along this y-axis, a translation along the z-axis. So let's see. And now let me see what it changes. It doesn't seem to change something. Oh yeah, it changed. Yeah, let me see. Yeah, it changes. Very nice. So a translation along the z-axis. Now we can also change the model of the robot. We can click right here on the upper left in file and load a robot, and right here we can choose the robot. We have a variety of models. Let's choose this one, a very simple one, and let's place other frames and changing the angle of the joints. Let me turn the robot arm to the screen. Apply a rotation on theta 1. Now right here. Strange the way that it is changing. It's kind of bugging. It's bugging, I don't know. But this effect is very interesting, and I wanted to show you this effect. Let me turn the robot to us, to the screen. Let me turn this axis just a bit. Nice. And now you will notice that this arrow in blue, it won't change its position and orientation, as we are right here applying a rotation about the z-axis. So look at this. Very nice, huh? Very, very nice. Let me just this frame, the frame of the two frame. Let me change these angles, and again, look this effect. The two frame, the arrow, the axis in blue color, it doesn't change at all. Very nice, huh? And when we do this algebraically operation of this operation algebraically, it's what we are doing right here. We are producing this effect. We are applying a rotation above this axis, and the whole body, the whole system, it changes, but this axis it remains without any change. What else can we do? Now this axis, as we are applying now a rotation above the y-axis, it doesn't change at all. And now, so okay, so x is in red, y is in green, and z is in blue. Very nice. Very, very nice. What else can we do? Let's change the 2, load the 2. No, let's get a more simple one. Even more simple. A hand with 3 fingers. Very nice. And Let's change the whole the robot as well. Very simple. Very nice. This one, very simple. So look, we can find the numbers of degrees of freedom, um, but right here you are not doing a rotation on the hand, which is the two. This way also we are not doing a rotation on the two, uh, but on Z, exactly on Z, very nice, very nice. When we apply a rotation around the z-axis, which is represented by this arrow in blue. Very nice, cool. I don't know. I'm a little upset with the results that we get on this example. So again, having more time, I will get back on this example to try to solve and get the correct results. But I'm following the same resolution, the same solution as is on the book. But okay, we need to move forward, and on the next video we will start to talk about Euler's angles. And for now it's all. Thank you for you that is following. Thank you for watching. Sorry if I'm saying something wrong. For you that is already know about this topic, about this content. Anyways, thank you. Bye bye.